All right, today we're going to look at section 8.3a, dealing with rational functions and their graphs. And our goal today is to identify asymptotes and holes for rational functions. So we've been looking at some basic just y equals a divided by x kind of graphs, and then we looked at some where we shifted them left or right, up and down. Today we're going to look at some different types and how we can determine what that graph should look like. So the first thing is a term called points of discontinuity. If a function has a polynomial in its denominator, its graph is going to have a gap at each zero of the polynomial. So anything that would make the denominator zero is going to cause some kind of problem. We call those points of discontinuity. The gap could be a one-point hole in your graph, or it could be the location of a vertical asymptote for the graph. A rational function is a function that you can write in the form f of x equals p of x divided by q of x. Just means that the numerator and denominator are polynomial functions. The domain of your function is all real numbers except for those values that would make that denominator zero. So here's three kind of typical shapes that we might see. The first one, the equation is y equals x squared divided by x squared plus 1. And you'll notice that this graph is what we call continuous. There are no breaks. So there's no points of discontinuity. Okay, there's nothing that's breaking that graph up. The denominator can never be zero. If you look at this denominator, we've got x squared plus 1. And if we think about setting that equal to 0, x squared plus 1 could equal 0, then x squared would have to be negative 1. And we know that when we square a value, we're not going to get a negative. All right, our second example is in factored form for us to make it a little easier. And this time there is a value that makes this 0. If we look at x plus 2 equaling 0, then x would be a negative 2. So if we had an x value of negative 2, it causes a problem because it makes the denominator 0. Now we call this a removable discontinuity, because we have matching factors here. We have an x plus 2 in the numerator and the denominator. So because we can cancel this out, it's considered a hole in my graph. Okay, that's important. If we can remove the discontinuity, if we can remove the problem, then it's considered a hole. It's just a single point that you can think of being able to remove just by filling the hole. Okay? So in this case, when x is negative 2, you will see here that there's a hole in our graph where x is negative 2. All right, for the third example, numerator is x plus 4, denominator is x minus 2. We look at when does x minus 2 give us a 0, and it happens when x is 2. But notice that there is no way to get rid of that. It will not cancel. So that leads us to having a vertical asymptote. It is a line. Notice our tick marks are going by 2s, so this first tick mark here is really x equaling 2. And it creates a vertical asymptote, a line that my graph approaches. You can see it approaching here and also approaching on this side, but it's never going to actually touch it. Okay, so we have a discontinuity that is non-removable. There's no way to get rid of it. Okay, so you will have these three situations. One where your graph is just continuous. There's no points of discontinuity. There's no values that make the denominator 0. Second one, we do have values that make the denominator 0, but we are able to cancel them out. So that creates the hole in our graph. And then the third case is where we have an issue with the denominator being 0, but there's no way to get rid of it. All right, so we have a couple examples here. We're just identifying, do we have any holes or vertical asymptotes? So for the first one, we have x plus 2. Does x plus 2 ever equal 0? Sure, when x is negative 2. So I look at that and say, do I have a way to get rid of that? So I have a point of discontinuity at x being negative 2. Since I can't remove it, it's non-removable, So that means it is a vertical asymptote at x being -2. Looking at our second example, we have two places. If x equals 3, we have a problem, and if x equals 4, we have a problem. So we don't want that to happen. Now, can we remove either of those? Yes, we can remove the x minus 4 piece. So this is going to lead to a hole, since it is removable. Since the x minus 3 doesn't have a matching factor in the numerator to cancel it, it is non-removable, so it is a vertical asymptote. Okay? Now, in order to actually figure out the location of the hole, we know the x-coordinate is supposed to be a 4, but we don't know what the y-coordinate is, and that is going to come in handy to be able to find that. So what we do is we look at the simplified version of this. If we cancel out the x minus 4s, we have an x plus 6 divided by an x minus 3. So we're going to plug that 4 in for our x values to see what we would get for y. So putting a 4 in the numerator would be a 10. Denominator 4 minus 3 is just 1, so my y-coordinate would be at 10. So the point 410 is going to actually be the little hole in my graph. All right, oftentimes you'll have to factor in order to see if anything cancels out. So always check if either the numerator or denominator can be factored. So let's look at our first example here. We could factor a 2 out, that common factor. Whoops. Take a 2 out and we have x plus 2 left. Looking at the denominator, we have x squared plus 6x plus 8. That's a basic trinomial. So we factor out our x squared into x times x. To multiply and get 8 and have it add up to 6, we would use 2 and 4, both positive. So we have 2 points of discontinuity. One when x equals -2, and one when x equals -4. Those are the 2 places that cause problems in my graph because they make the denominator 0. Looking at whether we can remove either of them. The x plus 2 does drop out, so this one is removable, which means it's a hole. Okay? The other one is not removable, which means it's a vertical asymptote. So we have a vertical asymptote at x equals -4, and we have a point of discontinuity, a hole, at x being -2. And again, to figure out what the y-coordinate would be, take our simplified version, which is just 2 over x plus 4, and plug a -2 in for x. That would leave us 2 divided by -2, or -1. All right, looking at our second example, we can factor a 3x out of the numerator. That would leave us an x minus 4 left. Now notice in the denominator we have a 4 minus x. That's just the opposite of x minus 4. So we actually can factor out a -1 from that and turn it into an x minus 4. So we have 1 point of discontinuity when x equals 4. That would make the denominator equal to 0. All right, it is removable. We have an x minus 4 for both of those, so we can drop that out. Because it's removable, it is a hole. So we have a hole when x is 4. And then if we plug that 4 back into our simplified version, well, our simplified version here is just 3x divided by -1. So y equals -3x. We put a 4 in here and we get -12 for the y-coordinate of our hole. All right, our third example is already factored in the numerator, but the denominator can be factored into x plus 3 and x minus 3. All right, so we have 2 points of discontinuity. one when x equals negative 3, and one when x equals positive 3. And looking to see if we can reduce any of those out. The x minus 3 is able to drop out, which means it is removable. So it is a whole. And the x equals negative 3 is not removable, so it is a vertical asymptote. So vertical asymptote at x equals negative 3, and you do need to write that as an equation. The whole is a point. Our x-coordinate is 3. If we look at our reduced version of this, we have y equals 2x plus 5 divided by x plus 3. If we plug a 3 in for x, 2 times 3 would be 6, plus 5 would be 11. Denominator, we put a 3 in and we get a 6. So something just a little under a 2. All right. So we've been looking at vertical asymptotes and wholes. We're going to shift now to horizontal asymptotes. It says determine them by comparing the degree, which is your highest power of the numerator, and the denominator. So we're looking at degrees. Highlight that, circle that. If the top degree is smaller, so we have less degree on top, more degree on the bottom, we have a horizontal asymptote at y equals 0. If the top degree is higher than the bottom degree, then there's no horizontal asymptote. And if the degrees are the same for the numerator and denominator, we use the ratio. So we have y equals the ratio of our leading coefficients, those coefficients of our highest power. All right, so looking at an example of each of those. For our first one, the degree on top is 1. We don't typically put that power in there. Let me try to move that over. It's not letting me. All right, so it has a power of 1. Again, we don't typically write it in, but it's there. So the top degree is 1 and the bottom degree is 2. My board's off a little bit here. So the top degree is less than the bottom degree, which means we have a horizontal asymptote at y equals 0. And you can kind of see that your graph is approaching that line y equals 0. Okay, so on this side it's coming down and approaching there. On the bottom here it's coming up and approaching from underneath. Okay, for the middle example, our top degree is a 2. Our bottom degree is just a 1. So this time our top degree is bigger than the bottom. We have more on top than we do on the bottom in the denominator. So we have no horizontal asymptote. And if you look at the graph, you can see there's no horizontal line that your graph is approaching. We're moving off to the side here, we're moving down here. They're not approaching any kind of horizontal line. If the degrees are the same, so in this case we have degree 1 for both of them, then we use with the leading coefficients. And those leading coefficients, in this case, would be a 2 and a 1. So we have y equals 2 divided by 1. We want the ratio of those coefficients, which just simplifies to y equals 2. And if you look at our graph here, where y equals 2, there is a horizontal line there that our graph is approaching as we move out to the outer parts of our grid. All right, so we're going to look at how do we find that horizontal asymptote. Make sure that we are looking at the simplified version. If it's in factored form, cancel out any common factors to make it a little easier for you. In our first example, notice that there's no x in the numerator. That means the degree on top is really x to the 0. It's not there. The degree on the bottom is a 1. So in this case, the top is less than the bottom, which means we have one at y equals 0. And I always think of it as the top being small and 0 is a small number. All right, middle example. If we think of getting rid of these x minus 4s that would reduce out, we really have x plus 3 over x plus 5. Again, our degrees are the same. They're both a 1. So we go to the leading coefficients. But in this case, the leading coefficients of each of these is also a 1. So we have y equals 1 divided by 1, which reduces to just y equals 1. Our third example is not factored, and that's okay for finding the horizontal asymptote. It's actually easier than factored version. Top degree is 1, bottom degree is 2. Since our top degree is less than the bottom, we have a less over more, which means we have one at 0. So horizontal asymptote y equals 0. Here our horizontal asymptote was y equals 1. And here our horizontal asymptote was y equals 0 again. All right, so let's try a couple from scratch here. If we look at it in factored form, we have 3x. Pulling that out, we have an x minus 4. We actually did this question already when we were finding vertical asymptotes and holes. Remember, we factored a negative 1 out of the bottom to turn that 4 minus x into an x minus 4. These drop out. We have y equals 3x divided by negative 1. Our top degree is a 1. Our bottom degree is 0. So we have more on top, less on the bottom, which we could see here. Top degree is 2, bottom degree is 1. So it's more over less. So we could actually find horizontal asymptote without even factoring it. So our horizontal asymptote, since the top is bigger, we don't have one. We say none. Okay, looking at the second one here, some of it is factored and some isn't. So you have two options. You can factor it all, which we did earlier. We had x plus 3, x minus 3. And then we cancel out the common ones. So we are looking at it in its factored form. In this case, our top degree is 1, our bottom degree is 1. So we go to the leading coefficients. So we would say we have a horizontal asymptote at y equals 2 over 1, which is just y equals 2. If you don't want to factor, then you would have to FOIL out the top. All right, so we had y equals 2x plus 5 times x minus 3. If we FOIL that out, we get 2x squared. Minus 6x plus 5x would be minus 1x, and then a minus 15. So we would be comparing that as the numerator and x squared minus 9 as the denominator. And you can see we end up really with the same thing. Our top degree is 2. Our bottom degree is the same. In that case, when it's the same for both the numerator and denominator, we go to the leading coefficients, which in this case, 2 over 1, and we're back to getting that same horizontal asymptote. So you can actually find the horizontal asymptote whether it's in factored form or not. The only problem is when part of it is factored and part of it isn't, you have to convert them to be both the same format. You really have to find that highest degree. All right, so in summary, we looked at points of discontinuity. All right, what makes the denominator 0? Okay, if it is removable, it causes a hole in our graph. If it is non-removable, it leads to a vertical asymptote. And your vertical asymptote is always going to be the equation x equals something. Your hole is always going to have an x coordinate, and then you have to plug it in to get your y coordinate. Then we looked at horizontal asymptotes, and we said that is based on degree. If the top is less than the bottom for the degree, then we have one at y equals 0. If the top is bigger than the bottom, there isn't one. And if the degrees are the same in numerator and denominator, we have y equals whatever the leading coefficients of the numerator and denominator are. All right, so let me know if you have any trouble with this. We're going to use these to help us actually construct some graphs tomorrow.